There we go. Okay, very good. We are going to start with an extremely scientific graph. Okay? So what I'm going to do on this graph is I am going to plot on the x-axis, I'm going to plot the number of lines of code, and on the y-axis, I'm going to plot frustration. All right? So I need you to understand that this talk is not about people like you. You're all like superstar programmers. You went to like, I don't know, like trade schools like MIT, like Jeff and people, places like that, right? So you're not going to relate to what's happening in this talk. So part of what I'm hoping is you also develop a little bit of empathy because you are all like experienced developers, many of you. And when you go out, you probably go out and schools come to you and say, what should we do? And you're like, just C++, man, beginning and end of everything. Okay, and I want you to develop a little empathy for how students actually work. Okay, so here is the typical student's experience. All right, they're given a problem statement and they have a blank screen, and somehow they have to magically fill up this blank screen with all kinds of incantations that are going to make that set of incantations exactly match what is given on the problem statement. This is actually a very intimidating task for a lot of people. So they start off with a very high frustration load, right? They don't quite know how to start. They mash at the keyboard or they call out for help or something like that. That's a pretty frustrating experience. And then they go for a little while, they program for a little while, and things seem to be going okay. And that's great, right? Frustration stays relatively low. And then they get to this point where they've got, I don't know, like about 70% of the solution, right? 80%. There's a few test cases that aren't working, right? And for many students, there's this sense of like, well, if this much code got me here, clearly a little bit more code will get me there, right? So I like to say that students are like 3D printers. They work only by additive manufacturing, right? It's like loss aversion is a thing. You have this too. You don't delete code, you comment out code, you put it in another buffer, right? Well, imagine somebody who's like every line of code was hard won, right? So then the frustration goes up and up and up, and eventually they come to office hours or something like that and say, my program doesn't work. What do I do, right? And by then it's usually a little too late. Okay, so here's what we are going to do. What I want, my sort of career goal in some sense, I have a high level goal, which is abstractions are the most beautiful things we have. They're also the most difficult things we have. How do we get people to appreciate and learn abstraction? That is my career goal. The low-level version of that goal is, how do we take this line that looks like, I don't know, some sort of valley and turn it into a plane? Okay? So I'm going to give you two parts to this talk, two things that we're actively working on to try to help with this. And they're all going to be at the left end of the screen. Okay? There are other things we can do at other points on the screen, but I'm going to start with something that is all the way over at the left end of the screen, in some sense before that first line of code has even been written. Okay, that's my first part. So we're going to talk about understanding problems before programming. Now, the way this works, I hate giving these talks because everybody just sits there staring, and after a while you pull out your phone because it's more interesting than I am. I acknowledge that. So what I want you to do instead is we're going to do what I do in class. We're going to talk to each other. Now, if you're extremely socially uncomfortable and you don't want to talk to anyone, that's perfectly fine. But for most of you, this is going to go better if you actually talk to someone. And even if you don't want to talk to somebody else, we're going to do some active engagement here. Okay? I'm going to give you tasks. What I would recommend is, if you're comfortable, turn to your neighbor and introduce yourself. Make a friend. Say hello to someone. Go. Okay, very good. So you've introduced yourself. Hopefully you'll remember their name. If not, ask them for their name again later. So here is the activity you're going to do with your neighbor or by yourself. Okay? So the exercise is, I want you to implement a median function. Okay? All right? And given a list of numbers, compute its median. And here's what I want you to do. I want you to talk to your neighbors and come back and tell me what could possibly go wrong. Go. 1 minute. And we're back. Okay, somebody yell out, what could go wrong? Yell out, someone. Huh? Off by one. Great. Another thing that could go wrong. Even number of elements. Another thing that could go wrong. List empty. Another thing that could go wrong. Sorry? Unbounded list. Oh, clever. Yeah. Somebody said something here. Come on. It's okay. Out of memory? Okay. What else could go wrong? Empty list. Very good. What else could go wrong? One last one. Different data types. One last thing. Indexing. Okay, good. Now, I just want to point out, by the way, that almost all of your answers reflect the fact that you're programmers and not students. Okay? And so let's talk about some of the things that can go wrong. Okay? So things that can go wrong might be not accounting for the empty input, very good. Okay? Or not accounting for even length lists, like which median you're going to get, the left median, the right median, the average of the two medians. We could spend like a whole hour debating this, by the way. It's one of my favorite topics to like argue about, but really ideally done over your stiff kind of favorite drink, alcoholic or otherwise. Okay? But what about if the input is not sorted, right? Or what if you are actually confused about median and mode or median and average? I said median, right? Like most of you, I mean, you're all like pretty much English-speaking people. You kind of know what the word median means. You may not, okay? So all kinds of things can go wrong. And most of the things here, actually all of the things on the screen have nothing to do with programming. They have to do with understanding the problem, okay? There's no like memory out of bounds. All those are valid concerns, but those are not the things that the student first needs to make sure they understand, okay? So what do we do? Students, in fact, there's a lot of literature. I'm not going to talk to you about all the research here, but students often solve the wrong problem, right? You give them a median task and they'll come back and give you a perfect implementation of mean instead, right? And you might think like, oh, and there might be some like learning objective, right? You might have wanted them to do a linear time median, which is a fascinating challenge. And they're like, linear time average, I'm done in like 5 minutes, right? I'm smarter than, Tony Hoare, right? But so there's all sorts of things that go wrong when students solve the wrong problem. And of course, we give them like auto grading. First of all, it comes too late, right? They've already finished the assignment. They finished the task, right? There's a fear of change, like, oh my God, I have to change all my code. Maybe I can tweak it. 3D printing. There's the learning objective that was lost, all kinds of bad things, okay? We generally focus a lot about programs, and we don't think about understanding problems. They're very similar. It's a Hamming distance of only 3 letters, but it's a pretty profound distance. Okay, now, ready for your second task? Everyone awake now? Yes? Yes? Okay, I wanted to hear more yeses. Yeah. Excellent. Okay, so the standard thing we do, teachers do, math teachers, everybody does this, right, is express the problem in your own words. Okay, why not just do that? That's how we check for understanding. The problem is students don't have better words, right? If you do this with a student, they'll basically read the problem statement back to you, but use some synonyms, right? Because they don't have better words than you, the expert, came up with. All right, so let's do a completely different exercise instead. Let's do a detour for a moment, okay? Forget about this problem understanding stuff, okay? I want you're all like software developers here. You've already proven it. So what I'm going to ask you to do instead is, again, you're going to do this with your neighbors. You're going to provide me with some examples, tests, input-output pairs for median. Go. Go, 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 go. Come on, come on. Okay, in 5, 4, 3, 2, 1. Come on, somebody yell out an example. Go. That's input-output. What's the output? Okay, next. Another example. 1, 2, 3 is 2. Excellent. Another example. 3, 2, 1 is 2 as well. Excellent. Another example. Empty list exception. Sorry? 194 is? 1, 4, something. Okay, excellent, excellent. I love that. 194 is a great example, and we're going to see why in a moment. Okay, another example. One more example. 0, 0, 0, 0, and 0. Okay, all right. Okay, 0 is all the way. All right, good. Okay, that is also like the grade some of you are going to get. Okay, so sorry. Now do I have your attention? Okay. So let me write a few examples. I'm actually going to pick up, in fact, at least one of these examples is going to be one that somebody here said, which is 1, 2, 3 is 2. Very good. Okay. 1, 2, 3, 4, 5 is 3. Okay. But then we get to an example like 1, 2, 3, 4. Right? What are the possible answers here? 2, 3, or 2.5 actually. Depends on which textbook you use. Okay? But, the young gentleman there had a really interesting example, which is morally equivalent to this one, which is what do you do here? What's the median, everyone? You sure? Isn't it the middle element? I actually have students who believe the answer is 3 because they've been told over and over in their lives the median is the middle element. Okay? All right. Ivy Leagues, what are you going to do? Okay, so here is the point. Examples are a concrete way of stating the problem in your own words. Okay? They happen. I'm going to use the syntax of a test case, but that's not really the point. The point here is that problem we were trying to solve of how do we get students to explore the problem and explore their understanding and state the problem in their own words, that's what we just did. This was not a detour at all. This was a solution to the problem. A solution, I'm not saying the solution. Now the problem is, some research by Kathy Fizzler and Francisco Castro shows that if they're inert, if you just ask students to write them, they won't write them. It's like, come on, I want to get on with the real stuff. Okay? So why not operationalize them? Very simple idea. Let's run the example against an implementation. Right? So we can do that. So here's what we're going to do. We're going to take this example suite. You notice there I've written median 132 is 3. Okay? And if I run this against an actual implementation of the median, it'll come back and say, I'm sorry, that particular input-output pair is wrong. Right? So this is great because now the student can ask, like, why is it wrong? Right? Maybe they have to go look at the textbook again. Maybe they're like, oh, of course it's 2. What was I thinking? Like, they never told me to sort it. Or maybe they're like, I don't know. They go to the TA and say, I really don't understand what's going on. The point is it's a constructive way to start that conversation. We're not talking like fuzzy words. We're trying to pin down meaning. Okay? So it's not meant to be punitive. It's meant to be a spur for discussion. Okay? So essentially what we're doing is we are auto-grading. Okay? But before any code has been written, notice what we are doing is not auto-grading the program, we are auto-grading problem understanding. Okay? But we can do more than that. We can run it against a correct implementation, but we can also run it against incorrect implementations. Right? We talked about the way students could get this problem wrong. Right? They might take the middle of the out-of-sorted list, they might take the mean, they might be mode, there might be other interpretations. So if I run this particular test suite on the screen against the correct implementation, it comes back and says, good. By the way, I fixed the 132 to be 2, right? Comes back and says, correct. Now, if I run it against middle of outer sort list, that is an implementation I can have, a bad implementation. It comes back and says, no, it doesn't pass. That's good, right? It confirms that I don't have that misunderstanding. It also confirms I don't misunderstand this with mode. But if you look carefully at the examples, I haven't distinguished yet between mean and median, right? So I don't yet know that the student understands the difference. This is a way to debug my student's understanding, okay? So we call this validity checking and we call this thoroughness checking. Ideally, the student writes enough examples so that they not only pass the correct implementation, they have a valid suite, but they have a fairly thorough suite, which is they also catch the buggy implementations, which is a way of saying, these are misunderstandings I do not have. That's what we're saying. We don't tell them that, but that's really what's going on. Okay? This is all implemented in an IDE for the Pirate programming language. So if you write, for example, median of 132 is 3, it'll flash a thing saying incorrect. This particular example does not match the problem specification. But if you write this, it'll say it's valid. But you caught only one of the buggies in there, right? We call these chaffs, my students call them buggies, so buggies is what they're called from now on. So we caught one of the buggies, right? If I write a second example that looks like this, notice now I'm really demonstrating that I understand it's not average, right? Then, then it comes back and says you've caught 2 of the buggies and so on, right? So there's this incremental interactive process, and essentially I pitch it to my students as like a 24-hour TA for problem understanding, right? You can do this anytime you want, and anytime you're stuck, now you have a very concrete thing to go and get help on. Like, why does this not pass? Or what am I missing? What have I not yet understood? Right? There's lots of user interfaces. You could have pop-ups. You could hover over each of these to get an understanding. There's any number of user interfaces. It's something we think about quite a bit. But the general principle here remains that we have tools by which we can automatically help students with problem understanding, okay? Which is like this big unaddressed problem. And Now, some of you, again, those of you who are software developers are like, wait, didn't you just say mutation testing in like a really long way? And yes, I did actually, except there's a very important difference, okay? In mutation testing, your goal is to generate as many mutants as possible. But of course, you have to worry about like, what some people call the oracle problem, right? Like, how do I know whether it's a true mutant or not? But also, there the goal is like to test a final test suite. Here, if I were to generate 1 million mutants and give it to my students, I promise they will spend the entire assignment period trying to catch the mutants and never actually getting around to writing the program, right? Human behavior, if you gamify something, that's the game they will play, right? And this user interface is particularly good at gamifying students, and it sort of traps them in this loop, right? We are not evaluating their test suite. We're evaluating their understanding. So we only want a small number of mutants, and every mutant has to correspond to an actual misunderstanding that a student might have, right? So we prefer to call this something like semantic mutation testing, which is it has to be about the semantics of the problem, not about all the ways the program can go wrong. Does that make sense? Like, developers making sense? It's like it's a distinction it's a qualitative distinction that also is quantitative, because I want to give like, the top 3 or 4 misconceptions. Right? So median and mode, for example, median and mean being kinds of misconceptions that people might have. Now, question is, of course, where are we going to get this? Well, obviously, right, experts curate these. They look at student experience and student questions that students have asked, et cetera, over the years. There's a little bit of a troubling thing here, okay? There's this phenomenon that's well documented in education literature called the expert blind spot. Experts don't know what they don't know. They have forgotten what they don't know. They don't know what people don't know, et cetera, et cetera. It's like you could almost call it the curse of expertise, okay? And unfortunately, most of us who are educators suffer from this curse, okay? Now, you might say, well, not my professor. My professor was a dud, but some of your professors were not duds and they suffer from the expert blind spot, okay? So the question is, how do we get around this expert blind spot, right? This is the classic like unknown unknowns, right? They don't know what they don't know. They do not know what it's like to be a novice any longer. So how do you make them simulate a novice? It's not very easy to say, in your own words, tell us what a novice would do. They've done their best, okay? It's a very clever idea here my student Siddhartha had, which is, here's the thing. Let's say a person writes an example and it fails. It's incorrect. There's all sorts of reasons it could be incorrect. There could be a typo. There could be a type error. They may have just like flubbed something like, oh yeah, whatever, right? But if you look closely at all of the failing examples, in there are buried the misconceptions. For example, if they say 132 is 3, there's a decent chance that they think the answer really is 3. And if several students produce something that looks like that, right, that means you have multiple people who genuinely believe that the misconception is the middle element, whether it is sorted or not. You see? So the failures in there contain the misconceptions. Okay? So what we've been working on is a new workflow where we gather all the failing examples, and then we're using clustering techniques. Now, here's the interesting part. You can't do naive clustering. Syntactic clustering doesn't work, right? Like your example, I believe, was 194, right? Is that right? 194? Yeah. And this one here is 132. They're exactly the same example, right? They're actually in the same sorted order, but they're syntactically miles apart, right? So what we need is a semantic clustering technique. I'm not going to go into this. That's like half a talk, and I won't go into what we do to do it. But the idea is you have to do some kind of semantic clustering. Then you can look for misconceptions, and you can translate those into buggy code. And then, that's basically a program synthesis problem. It's not one that the synthesis community addresses because they only inadvertently produce wrong solutions. They don't advertently do so. We need them to explicitly construct wrong solutions. And it's a little, it's an interesting challenge question. Okay? And I'm going to show you a little example, a little evaluation of how this technique works. So I'm going to show you some Venn diagrams, a pair of Venn diagrams. In each case, we're going to have a circle for what the staff predicted, which is this left blob, which is yellowish, if you can see the color. On the right is a blob that's bluish, and that's like what the data reflect. Okay, and what we're hoping for, of course, is like the blue is contained in the yellow, right? The experts caught all the misconceptions, right? That's what we're hoping for. Here is one problem where we did this detailed manual analysis. The staff predicted a total of 5 misconceptions. The data showed a total of 11, 3, 2, and 9. Right? So 9 of these were in the data that the staff had not missed. That's like almost a quantification of the expert blind spot here, right? And this is very actionable because those 2 we definitely want to keep. The 9, we might want to add some from there. Then these 3, maybe we don't need to keep around, right? Maybe they're not as useful, right? And maybe we can drop them and replace them with something where the students actually do have that mistake. Here's another program, a different problem, where there were a total of 17 on the right and 7 on the left, and only 1 was in common, right? So again, expert blind spot quantified. Experts have a whole bunch of ideas of what students are getting wrong, and students are making a completely different set of mistakes. Okay? All right, so this is a sort of technique. It's like crowdsourcing except with students, so it's like, class sourcing, and it turns out to be a very effective way to find misconceptions. You just look at the failing examples, gets around the blind spot, and it's also very lightweight because the students in particular, are not having to do any extra work they weren't doing before. Right? We're not saying, oh, come in for an interview, tell us what you are thinking, etc. They're just doing stuff that's helping them write their programs, and along the way, they're generating data for us to figure out what they might be getting wrong. Okay? All right. So that is the summary of the first technique, right? So students program before understanding the problem well. They don't have tools to help them with that. We would like lightweight ways to undo problem understanding so that the students are actually solving the problem we want them to solve and not some other problem. And there are lots of good reasons like recall issues, cognitive issues, why they might solve the wrong problem. Examples are a good way to operationalize this. We can use the semantic mutation testing technique, and even better, we can also mine their mistakes for insight that then helps like the next generation of students. Okay? That is the first part of the talk. Okay. Now I'm going to go on to the second part. So you remember, again, I put up this graph, and I said, we're going to start over there, right? Before any code has been written, let's make sure we understand the problem. Okay? The second part is, let's move that blob a little bit over to the right, okay? Which is, can we get students to do some kind of planning? All right? Now, for this part, I'm again going to give you a task. This time, you finally get to write some code. Okay, you can pick any programming language you want. You can do whatever you want. I really don't care. I'm going to put up a programming problem. A handful of you have probably seen this problem before. Rest of you can sort of figure it out. Okay, here is the problem. I'm going to give you an input like an array, list, whatever data type you prefer. And what I want you to do is I want you to produce the average of that list. Okay, but I only want the non-negative numbers. In fact, I only want the non-negative numbers before an optional -999, like a sentinel value, okay? This is called the rainfall problem. The idea is this is meant to be like rainfall readings, so you want to figure out the average rainfall. The negative values are like there's a faulty sensor, and -999 means that's when we cut off the stream, okay? And you don't care about data. So in fact, in 2010, there's Mark Gosdale's a very well-known computing education researcher. Now this problem, this rainfall problem, is kind of notorious. It was first published in about 1984 by a guy named Elliot Soloway, and he was trying to use this to understand how students plan solutions. Okay, the problem was nobody could implement it correctly, so he never got around looking at planning. He's like, I don't know what's going on. Nobody can even implement it, never mind what kind of plan they use to implement it. Now, you gotta, he's at Yale, so what do you expect? But unfortunately, they tried at other universities, didn't work there either, right? In fact, it became notorious as the unsolvable problem of introductory computer science. Now, you're all sitting here saying, that is ludicrous. How can this not be a trivial problem, right? I mean, Ramsey's second test case would have caught the bug and he'd have flipped the lines of code and we'd be all set, okay? So how could this be hard? Which tells you something about your understanding of CS1, okay? Novices actually find this hard. So it's so bad that 20 years of replication found that nobody can solve this problem. Mark presented it as a challenge. He said, after 30 years, why hasn't somebody beaten this stupid problem? In fact, what if we would like to design a course around solving this problem, right? Like maybe just set that as a goal, right? He's got this little thing at the bottom. Maybe these teach scheme folks might be able to solve it, but who knows? We'll see. So let's talk for a moment about why this problem could possibly be hard for a novice, okay? There's actually a lot of things going on in this problem, lots of moving pieces, right? There are basically about 6 different tasks, right? There's an act of truncating at the sentinel. You have to figure out what to do with the negatives. You got to sum it, you got to count it, compute the average, figure out what to do with the empty list, right? And all of these things are sources of bugs. And if you're a beginner, trying to do all of these together can be pretty overwhelming. So in 2014, Kathy Fizzler published a study where different places were using how to design programs. And what she found was actually students can do fine, right? And students who had a clear structure of their programs had far fewer errors. They made good use of built-in and higher order functions, Ramsey, okay? And they showed a much greater diversity of structures than in traditional imperative programming. Now, one of the things that's interesting about this is you can think about whether you want to do this. Roughly speaking, there are sort of 2 to 3 major structures that people use. One is your structure, which is a single loop. Another is a parallel of yours, which is to do 2 loops, same idea, but 2 loops. And the third is basically what we call a cleanse first solution, right? Basically look at the problem and say, this is essentially an average. How can we turn it into an average problem? Right? And if we truncate and then clean, now we turn it into an average. So let's cleanse the data and reduce it to a solved problem, essentially. Okay? So these are the 3 large-scale strategies. And she saw students using all of these strategies and basically succeeding at this problem, right? Mark actually said this beat rainfall, whatever that means. Okay? So we've been studying these kinds of questions since to try to figure out how students plan programs. And we've got like a whole family of problems that we've been trying to come up with that do this. But all of these studies have a certain weakness, which is what they do is they ask students to write the program and then try to figure out what plan the student used, right? But now that we can have students solve these problems, we can go back to Elliot Soloway's dream, which is actually focusing on the planning part, right? Like, ideally planning is something that happens before the solution, not after the solution. The urban planners here might say, haha, good luck with that. But, yes, at least in principle. So what if we go in the forward direction? What if we get students to write plans first? Okay, all right. So now I'm going to give you an exercise. And the exercise, don't worry, there's no programming. So the exercise is, imagine, a place you live or a place you work, office space, home space, whatever. Okay, draw out a little floor plan for me. You can do it in your head, you can do it on paper, you can do it on your computer. I'm going to give you a minute to draw a floor plan. Go. Okay, so let me ask you this. Does the floor plan that's either on paper or in your head, does it look kind of sort of like one of these things? Roughly? Yeah? Okay. There's the thing on top right is, called a studio apartment, or in Brooklyn, I guess you call it a palace or something like that. But it's this general idea, right? Now, in fact, these are all pictures that I took off, random, websites, like apartment building websites. How many of you are actually trained architects here? At most 1 person, 2 maybe? Yeah, 1 person. I mean, like building architect, by the way, not like computer, but building architect, right? Good. Okay, notice the rest of you didn't even try to put up your hand. You're like, haha, I'm a software architect, right? You didn't even claim to do that. And yet you're able to understand this floor plan, right? They expect anybody to be able to understand this floor plan, right? Because there's a common vocabulary we have, right? We have the shared vocabulary that we picked up. None of you went to architecture school. You didn't take an architecture class, but you're like, that slidey thing, that's like a door, that's a window, that's a wall. We have this common vocabulary, right? And so planning is something that benefits from having vocabularies, okay? And The other thing that's interesting about planning is that we don't just use a single notation, right? So here, for example, is, falling water, and here is the floor plan for falling water. Here's like an elevation sketch of falling water. And in fact, if you talk to the architect, you'll find like there are several notations that architects use before they go off and build the building, right? Now, I mean, I put up falling water a little ironically, right? Because Frank Lloyd Wright was not the best like civil engineer in the world. But the point being that even Frank Lloyd Wright didn't just go off and start building buildings. Even he engaged in a process of thinking through several steps, not only multiple stages, but also multiple representations, right? We look at the problem from several different perspectives. Or here, for example, is the original Apple mouse, the infamous single button mouse, right? And here is from the patent of the original Apple mouse, right? We've got, again, multiple stages, multiple representations, and each representation talks to a different person in a slightly different way. And so planning and design are these multi-representational, multi-stage activities. Kind of like wonder, where is that in programming? Now, of course, there's somebody in the room who's like, UML, finally. It's like, yes. And in fact, this is actually the point in favor of UML, right? It does give us different representations, does give us multiple stages, does let us talk about a program at some level of vocabulary other than lines of code, okay? I didn't think I'd come here and defend UML, but here we are. Okay, so what is our vocabulary? So we're proposing that one vocabulary is higher order functions, okay? And there are I found that there are kind of two ways to think about higher order functions. A lot of people's introduction to higher order functions is like abstractions of code, right? Here is a traversal pattern, and you write it over and over, and we're going to call this the map pattern. Here's a traversal pattern, you're going to write it over and over, and we're going to call this the filtering pattern, right? But another way to think about it is more as like units of abstraction in their own right? They are abstractions of behavior, and there's a sort of uniformity that they represent. And this is the point of view that I'm trying to push and trying to like figure out how to train people on. So we'll do this as an exercise, okay? I'm going to put up an input-output pair, and you are going to yell out a higher order function. Everyone ready? Okay, I'm going to put out an input-output pair and immediately free associate, yell. Ready? Ready? Yeah. Yes, okay, go. Good. Looks mappish, right? Okay, there's sort of trivial map, okay? Okay. Good. See, you already know how to play this game. Okay, so as experienced programmers, you have this vocabulary in your head. You have this ability to recognize from one example. You're all like one-shot learners here, right? One example, and you're able to like even point out the ambiguity when there is an ambiguity, okay? So I want to get it so that every beginning student can do just as well as you do, all right? And so essentially, if you think about this, like there's a space of ways in your head. There's probably some kind of complicated decision tree, which probably involves things like what is the output type, and like some case it's list, some case it's Boolean. What kind of an element type? Is it the same or is it different? Is the output length the same or different, etc.? And you use all of these criteria to try to help you figure out like what kind of thing you are dealing with, okay? So what I'm trying to do, our current project, is to basically, we need a notation for talking about these plans and designs, and I'm trying to elevate higher order functions to being that notation, okay? Now, if you look at that picture, you might recognize that this looks a little bit like Scratch, which is a programming language that's a lot of kids end up programming in these days as their first language. And this is a variant of Scratch called Snap, and we've been working with the Snap team to be able to build our own little custom Snap environments. And so it takes very little effort to build a custom Snap environment where the only thing you get is like higher order functions, okay? And we've been having students try to plan out their programs using these higher order functions before they write code. And I'm going to show you for one program, there's actually like, here are 3 different plans. You don't have to read the details. What I want you to appreciate is 2 things. First is, one of the things I like about Snap is you can actually put text inside the boxes, right? That's kind of like not where code ends up being, but it's actually really useful for us because you can bottom out a text wherever you want, right? You can plan the outer structure of your program, right? Which is what Ramsey did, for example, right? He planned out the outer structure, and then there was some like textual details, like, and then at this point, what does it do? It like truncates at something, whatever, right? So you can write text, but also these are three different solutions for the same problem, and you can see like the first one is a filter and just text, right? The second one's gone one level of resolution deeper, a filter with an and map. Third one's a filter of an and map with like different details inside of it. Right? So we're finding this to be a reasonably flexible mechanism by which students can express their plans. We can also give them some high-level checking and say, you know, if you think a filter is the outermost operator, that's just never going to work, right? So trying to figure out how we can give students feedback. Of course, in a dream world, we would then take the inner text and feed it to like, you know, GPT and get code and try to run it. We haven't had any success getting GPT to produce useful code in this setting. But, you know, I think down the road, and you know, if somebody gets provoked by that statement, wants to show me that I'm wrong today, that would also be welcome. Okay, so where are we going forward with this? We're trying to study a few more things here. For example, left entirely to themselves, what representations will student use, right? Like just if you just say free-form plan, what are they going to do on paper, computer, whatever? We've been trying out experiments where we give them textual notations and diagrammatic notations and see which one they prefer. What do you think would happen, text versus diagram? Diagram, right? Yeah. Overwhelmingly text. Overwhelmingly. It's like diagram's not working in the slightest, which is weird because I think most of you would probably draw a diagram, right? So is it they're not comfortable with diagramming? Is it like, I don't know, kids these days don't know how to use paper? Like, it's not entirely clear, but it's also, you probably have some sort of visual notation you've built up that's probably your own personal visual notation. They probably haven't gotten far enough to build up that visual notation yet. I don't know. We're trying to figure it out, right? Also, will they do things like organize like a recipe like 1, 2, 3, 4, 5? Will they draw text in like more, you know, indented ways? We're trying to figure that out. And in some sense also like what is the split between programming and planning, right? Because, you know, I've sort of presented like, well, you know, Frank Lloyd Wright did that, so obviously we must all plan before we build anything. But we know that that isn't quite how programming works, and we're trying to understand like what is that iterative loop? What is that mix of things? Okay. So there's lots of papers. I'm not going to expect you to read any of this. There's lots of papers. If you want to, you can go look at the titles later. And what I want to do is to have lots of time for discussion. So I'm going to end my talk now. As a reminder, we started off with this analysis of a problem. And the analysis of the problem is programming is harder than we think. Okay, especially for novices. And I gave you I made some jokes about 3D printers at the beginning, but I gave you this rainfall problem later on as concrete evidence. There's lots of problems like this of concrete evidence of students having difficulty writing programs that you might think are trivial. Okay, I then showed you one solution to this problem, which is try to make sure they first understand the problem so that they don't spend all their time frustrated. Another thing is to try to talk about planning tasks before they do programming tasks. And those are the two parts of the talk, and you're welcome to reach out to me. And I am now happy to take all of your questions, comments, criticisms, and everything else that you have. Thank you. Bring it on.
So I really love the section about understanding problems before programming. It reminded me of some of your earlier work. I think you called it mystery languages.
Yeah. Oh, yeah.
And for people who don't know, the idea was that there was these languages that weren't described to the students, and then they had to come up with like inputs that would show off the differences between these very subtly different interpreters.
Oh, yeah.
So that has me wondering, or suspecting, I guess, that you've applied the same technique to much more complicated domains than median. And I'm wondering what surprising insights and misconceptions you've found in some of the more advanced applications of testing understanding like this, I guess.
Wow, you give me a lot of credit that I'm not sure is deserved.
Like 15 papers
let me tell you about the mystery languages because it's kind of a fun thing, right? We're trying to teach people about, so this is something we do in my upper level programming languages class where we're trying to teach like semantics, right? These are people who know how to program, or at least they think they know how to program and they come in. So we're now talking about like principles of organization of languages and things like that, right? And so the way we structure things is we go through a sequence of features that get incrementally more interesting. So you start literally with numbers and work your way up from numbers to like functions, higher order functions, continuations all the way, right? But the point is in every one of these features, there's variation between how those features are represented, right? So when you say objects, right, we all know like the word object means about 17 different things depending on which language you're in, right? Even a function call means different things. Fortran and COBOL function calls behave differently than function calls do in like modern programming languages. So in the mystery language idea, what we do is we give them an implementation, you write a program, and you run it, and you don't get one answer, you get like 3 answers. So if you're at 1 plus 2, it'll say 3, 3, 3. Okay? You say 7 plus 5, it'll say 12, 12, 12. Your job is to come up with inputs so those 3 answer outcomes are not the same. You're just given a syntax, and you have to reverse engineer the semantics, right? So for example, if you say 1 divided by 0, you might be like, in one case you might get like infinity, in another case you might get nan, third case you might get like 0, right? So now you've told them apart. And the idea is to treat this as the sort of a scientific method, right? An experimental process where you construct a theory, you generate an experiment based on that theory, figure out what it does, and then refine your theory and keep revisiting your theory. That's the idea behind mystery languages. So we are actually looking at how to combine these things more. That, in some sense, that is writing examples for problem understanding as well, except the problem there you're trying to understand is what is the semantics of the programming language. And that's a little different from this in the sense that you're trying to find differences that are relatively small, that to most people you might not even observe them, but when you do, they are very surprising and shocking when they happen. There's a very robust theory in cognitive psychology of what is called the theory of contrasting cases that says it comes out of perceptual psychology. And essentially what it says is that oftentimes the best way to understand something is to see a bunch of similar things and just focus on how the little things are different rather than trying to understand an atomic thing in itself, right? So we don't use contrasting cases over here. Because we're not trying to get at subtle differences, right? I don't want you to understand like minute differences. That's what like mutation testing is good for. I want you to understand like high level difference in median and mean, right? But when you get to these semantic features, so I think the thing is it's the same set of ideas, but the way you express the ideas has to be very different, because in one case you're interested in broad stroke differences, in another case you're interested in fine grained differences. The broad stroke differences are to get started. The fine grained differences are if you want to become a semanticist, like your whole life is one of pedantry, right? It's all about fine grained differences. So does that make sense? You are exactly right to see that there's a deep parallel between them, but the methods are slightly different because the goals are slightly different. Does that make sense? Yeah, thank you. Great question. Hello.
Hi. So 2 questions about Pirate, which looks fascinating. First is, are there capture methods built into the language, or is it just students turn in all of your guesses and iterations? So that's question 1. And question 2 is, so what's the life cycle like after students learn on Pirate? Do you switch them to Python next? Like, what happens to them?
Yeah, that's a good question. So to answer your first question, actually, so we do the logging of examples in this system, but the Pirate language itself is very explicitly privacy respecting. It has been deeply tempting to log every damn thing we can. In fact, we log nothing. Okay, I don't want to know about your programs. I want you to be like, I don't want a student to feel like, oh my God, somebody's watching over me and that's going to affect my performance. This has been very useful for us because I also co-run one of the largest middle school outreach programs in the US. And thankfully, school districts, unlike a lot of other people, care about privacy. They have minors, right? So we get school districts who contact us and say like, we are interested in your curriculum, but like, what's with student privacy? And everybody else is like, we log the shit out of you, right? Because analytics. And we're like, we log nothing, go for it. And they're like, thank you. We've gotten like badges of excellence from various school districts. Like, this is what we wanted to hear. And that is, as a researcher, it's like, okay? But I have to decide whether I care about students or my research more, and I care about students more. We're looking a little bit about like how we can try to reconcile that a little bit. Like, like maybe we can log some like statistically log events, things like that. There's a bit of a movement of this sort of thing. Like a good question is like, what should FOSS systems do, right? What should free and open source do? Logging is useful for finding problems, right? The trick is when the logging coincides with identity, right? But if you don't log with identity, you can't track longitudinally what a student is doing. It's super hard. It is much harder than my small brain is capable of dealing with. So and like all of the Pirate team, Ben Lerner, Joe Politz, and I all came out of doing like web security research. So we knew all the ways things can go wrong. So I like first do no harm, right? Yeah. So your question about the Python question is interesting. So we have a book called Data-Centric Introduction to Computing. And the whole point of the data-centric introduction, we start with a whole bunch of stuff this is all like in Pirate. But then when we get to programming in state, we actually do something interesting that most books don't do. We use the two languages in parallel, okay? And the reason is we want students to learn how to transfer ideas from one language to the other. And transfer is one of the most robustly difficult problems in all of education, not just computing education. So for example, when you look at state, you look at every one of these programs in both Python and Pirate, okay? And you see how to write these things both in Python and in Pirate. You get to see like, each language in its own right. You understand a little bit about strengths and weaknesses. Pirate syntax is very explicitly designed to make a distinction between variable mutation and structure mutation, which is something most languages screw up, and that causes all kinds of confusion for students. So, like over here, right, there's this weird syntax here that says, here you just put an equals, here you just put an equal sign to do the mutation, but here you have this funny like bang colon thing going on to make clear that you're changing this field of that object, right? So it's very carefully thought out. We're doing a bunch of research on these transfer issues, and the book is basically a research-driven project. Okay, does that answer your question? Thank you. Next question. Hello.
Hi. I'm curious. You showed us planning in the small for tiny functions, and of course, as students progress, they write larger and larger programs. And for us in the audience, some of us are writing huge programs and planning entire architectures or whatever. I'm curious, what parts of these ideas stay the same as you get to larger programs? What parts change?
That's a great question. I'm going to give you a terrible answer, which is I don't even want to think about that. Okay, and there's a reason, right? Like I like it's same thing with like Pirate, right? It's very easy to build a programming language and then say like, oh, shiny thing, oh, another shiny thing, and add every shiny thing. We have a very clear focus on what Pirate is for, and almost definitely it's not for other things, right? If people can figure out how to use it for something else, that's great. If they want to send a pull request, we might consider it, like it's happening right now. But by and large, we just don't want to know about it. Right? We want to do like drill the thing we do really, really well. So the same way, like I have obviously as somebody who's built large systems, deployed large systems, I have opinions on these things. But there's a lot of other researchers out there. Like you open like any software engineering conference, like half the papers about this sort of thing. I don't feel the need to add to that. Right? I want to take this problem and nail it and let everybody else who's nailing those other problems nail it. How's that for a terrible but like very honest answer?
All right, two more questions.
Back there. Oh, yeah. Sorry, please. Yeah.
No worries. So it's interesting you were talking about the interchange between planning and writing your program and how you go from, and I was reflecting on the way that I came to my solution. And the first solution that I came to in my mind was definitely the two loops that you mentioned. And after I wrote it down, having it on paper, I was able to look at my solution, and maybe within the last 5 seconds, I was like, "Oh, I just moved this into the first loop. And you can just loop once."
Yeah.
But I think part of what was going on there is once I was able to see it on paper.
Yeah.
The structure was emergent to me, right?
Exactly.
The plan, like kind of the way our eyes fuzz over, and you're saying like, as an expert, you can see the plan in the program.
That's right.
And it was able to easily move one element in.
Right.
But yeah, so I'm wondering like that planning programming loop back and forth.
Yeah.
Any thoughts on how students might do that?
Yeah, this is our next big research question. I don't even want to speculate because I don't know, and I would just be guessing just like you would. Your guesses are probably better than mine. So, but this is the thing we are trying to figure out. Like we think everything's going to be planned before every programming happens. Similar thing with testing, right? Like what's happening is we split testing into two parts. Write examples to understand the problem, which are still test cases, and then write the rest of your test suite. You still have to do that, right? But here, I think it's going to be even more iterative, just like real testing is also more iterative, right? So yes, and I don't have any scientific answers to your question.
I guess I was curious about the tactile representations of plans that you had mentioned earlier, and how students kind of come up with their own. do you think there's value in either optimizing like the existing like block-based solution that you worked on for tactile representations, or maybe just like drawn representations?
Yeah.
And kind of as a follow-up there, I'm just curious on like if students have come up with their own like notations that you're like familiar with that you've seen like patterns in other than like the text and recipes that you had mentioned.
The latter, so the former question, I don't, Zishan, there's a hand up there, by the way, right back there. So there's the former, I think it's premature for us to optimize. Now, you're pointing out, of course, something very significant, right? If you have a non-optimal representation, people might not use it. And if you'd optimize that representation, maybe they'd use it all the time. And it's sort of a resource issue for us to figure out where to optimize. But I think I still want to do more qualitative, formative research to figure out whether that block-based solution is even appealing to them before spending time on it. Right. So I don't know. As for the second no, it's nothing yet. Nothing's emerged. And we're seeing like, we've got like hundreds of these, and all we know is like nothing other than like this sort of checklist, the recipe list kind of thing. But that's probably driven by an example we showed them. So it's very hard to tell. And what we need is an iterative loop where we generate like, here are 5 different ways you might imagine writing a plan, and then see what they come up with, and then like keep parsing that space apart. Yeah. Thanks.
I'm thinking about your first and last slide about the graph of like frustration over time.
Yeah.
Which I thought was really cool.
Yeah.
To a certain degree though, like, some amount of frustration is still inevitable.
Yep.
And
good. Productive struggle is a well understood theory in education.
Ooh,
yep.
Yeah, sure. Okay, so to me personally, and anecdotally, like from my friends, it seems like one of the aspects of programming is the development of like an emotional skill around not reacting to problems with excess frustration, or not letting it like restrict, or like cloud your judgment and like.
Yep.
So yeah, like, how much of that development of that emotional skill is within the scope of like a computer science education, and like what are ways
so
that you
this
can
is
help
great.
students on that path?
It's a great question. It's absolutely critical, and I think we have a tendency to focus too much on like both technical and cognitive aspects and forget the whole sort of emotional aspects and social aspects. Okay, so you're completely right. Now the thing is, there's also some reasonably good research that shows that like students, so I'm going to draw a graph for you. Okay, this is self-efficacy across time. Okay, and students, and this particular study was looking at male versus identify as male versus identify as female students. Okay, lots of issues with that, but just take some large scale. So here's the graph. Okay, everybody starts off down here. Basically, everyone ends up kind of up here, but the males go like this and the females go like this. And the females get to this point, they drop off. So what's left is the females who actually were willing to brave through it. Okay, so the thing is, you notice that I didn't draw a flat line as my goal. My goal is still like bumps, right? What we have to do is to make those bumps not so overwhelming that the student stops. And then what we have is this huge survivor bias where like, yeah, I powered through it and it was okay, but we don't hear from the others, right? So I think what I'm hoping to end up with is like a collection of technical, cognitive, and social and emotional aspects so that we can achieve that kind of goal. So we have like productive struggle and not unproductive struggle. You're absolutely right. Last question. Okay.
That was great.
Good.
Thank you,
She's shutting
Shriram.
me off. Thank you. Bye.
Thank you, Shriram. Thank you so much.